Hi everyone, I'm Khooyooz from Heidelberg University, Germany. I will present our paper accepted in ISCAS 2026 entitled CryHop, Baby Cry Classification on Dataset, Dunstan Dataset using Transfer Learning and Ensembling. You can find the paper using this QR code, or you can email me to discuss about the paper if you are interested. The outline of this presentation is an introduction to different baby needs and the reasons why they are crying, the dataset that we have used, our methodology, experiments and results, and finally we discuss about the results and conclude the paper. So why is the baby crying? There could be different reasons for the cries of the newborn babies. Maybe they are hungry, they are tired, and they are in a discomfortable situation. This is especially challenging for new parents and babysitters because at the beginning they don't know the reasons and they are not familiar with the type of cries. So in this research, we aim to develop automatic detection of these cries. In 2013, Lady Priscilla Dunstan had recorded a video and made a theory that she has discovered 5 different cries of the babies. So she had 5 different babies and introduced 5 different reasons for their cries. The total sample number of this dataset is 196. The average duration of these audio samples is 0.77 seconds. The sampling rate is 16 kilohertz, and the audio samples are extracted from Dunstan video corpus. So this is a short video of introduction to these different cries.
All newborn babies communicate by using 5 universal sounds.
The first word is ne,
Ne.
and this is the word for hunger.
What's the next word?
The next word is ow, and that's the word for sleeping.
Very good. Now, you've uncovered a word that you say means discomfort. What is that?
Yes, this is the word he. The next sound is air, and this is the lower sound. So one is, and this is when there's an air bubble in the top part of the chest and the body's using a reflex to get the air out.
All right, so
All new.
Yeah, okay. So what is the research gap and why we found the need to do further research on this topic? So the previous research and papers on baby cry classification had the problem of lack of enough information for reproducibility of their works. So they didn't mention all the parameters that they had used in their pipeline, and the other researchers were not able to continue their work. Also, there was a problem in the lens, actually introducing the inputs to the AI models. So because the samples, audio samples, were not the same length, they had to zero pad the audio samples which were smaller than the average or than the fixed size that they were introducing to the AI models as input. So they need to zero pad the audio samples, as you can see here, to make it compatible. And this zero padding introduced a lens bias, as you can see here, by looking into GradCam images, which are standing for gradient weighted class activation mapping heat maps. We found out that the models are not attending to the information of the audio samples themselves, but they are attending to the edges, which is a big mistake and lens bias, actually. And also some works, they had a lot of data leakage, and they were introducing the train samples into the test samples, and in the inference part, there was a unfair classification happening. Also, there were some works that they were segmenting the data, and for example, in the Dunstan class, then the Dunstan dataset, there were 3 classes ending with EH sound, which in which segmentation kind of makes a confusion, because if you segment, for example, this one, you segment it to, for example, one part H and one part EH, and this second EH is similar to the, let's say, first class, and in the third class, this second EH is similar to the second one, and this would be a confusion and is not acceptable, and whatever comes out for the results are not reliable. So our methodology is based on Mel spectrograms, which converts the audio samples to time frequency images, and based on variable Hop lengths. And we would be using VGG16 as our AI model. By fine-tuning this AI model, we will be inputting the Mel spectrogram images to the AI model and classify the baby needs. The processor that we would be using is 64-bit Core i9 Intel CPU system with 32 gigabyte RAM, and NVIDIA GeForce RTX with 8 gigabytes of GPU and PyTorch framework with code acceleration. So imagine that we have an audio sample X with N samples and a window of length L and Hop length of H with the target frame of T and DFT size of N FFT. So the spectrogram, the actually short time Fourier transform would be defined as relation number 1, in which we can see the audio sample xn is windowed by Windows W, and this is also the length of the window is kind of controllable by this Hop length, which you can see here. And in relation number 2, we take the amplitude of the SDFT transform, and it becomes spectrogram. By applying a filter bank of M, and K, we bring the spectrograms into human perception and into ranges that are kind of similar to human perception. So in relation number 4, we take a logarithmic transform on spectrogram, Mel spectrogram images, and this brings the signals, the images into a more, let's say, into a better dynamic range for the AI model. And here in relation number 5 and 6, we can see the relation between the target frame T and Hop length H. So we wanted fixed size images to be inputted to the AI model. So we wanted to t be fixed. So here, by changing h, we would have a fixed t. Okay, so these are some parameters that we will use for producing our Mel spectrogram images. Because the VGG16 has been originally trained on big dataset ImageNet, and the inputs were 224 by 224 and in 3 colors RGB. So we also replicate the produced Mel spectrogram images, and we resize the 32 by 224 Mel spectrogram image to 222 by 222 and replicate it 3 times to make it compatible to VGG16. So these are some of the images which we have created using our method. And for example, this one stands for belly pain, discomfort, and hungry. So this is the architecture of the model that we have used. So we remove the fully connected layer from the VGG16 itself because it's a huge fully connected layer which has been trained for 1,000 classes, but we have only 5 classes here. So we remove it and customize it for ourselves for the 5 classes with very lower number of, let's say, nodes here, as you can see. And so we unfreeze the last convolutional layer of the VGG16 and then train the whole model with the inputs and with the labels that we have end to end. So the experiment, we do nested cross-validation with inner fold ensembling. How it works is we have a 5-fold cross-validation in the outer training set, let's say. And out of each 4 folds, we create another inner cross-validation in which we take, let's say, so this is not, yeah, there is a small problem here. Should be 5 models, but anyways, so from the inner fold, we create 5 models, and using these 5 models, we use voting and ensembling them to predict the last fold, as you can see here. Okay, and we repeat this 5 times, and then we would have a nested cross-validation. Okay, so as for the results, we report top 1 and top 2 classifications. For top 1 classifications, we achieve around 95% of accuracy with F1 score of 95. And for top 2, we achieve around 99.49%, let's say 100% of accuracy. And this means if we cannot address the baby needs with 1 shot, we can definitely address it with 2 shots. So these 2 are also the accuracy and loss curves of the training. And compared to the previous works, our work has relatively achieved better results. So as you can see here, we again had a look into the GCAM images, and this shows that our model is attending into all parts of the input signals instead of just attending to one special part, like the lens bias problem that we had earlier. And for example, for air lower gas, the model is kind of attending to all frequencies. For EH sound, to higher frequencies, here to lower frequencies, here to again lower frequencies and the first part of the sound, and here kind of more attending to the middle frequencies. And this simply shows the model is learning based on the variable Hoplands method, and this is kind of making a fair classification. So as mentioned, GCAM images confirm Hop method is valid. We had some failed attempts and also found some failed attempts in the literature, like looping, zero padding, noise padding, stretching, and speeding up the audios, and also segmentation. And we found out ensembling improved the overall accuracy compared to the simple inference. So just instead of doing 5-fold cross-validation, nested cross-validation using ensembling kind of helped to improve the prediction by using the prediction of other models instead of just relying on one single model. For future work, we aim to develop an Android application to kind of realize and implement these classification real time. And because VGG16 itself is a relatively heavy model, we aim to make it more lightweight using, for example, Tensor TF Lite model. And this would reduce the power consumption and increase speed. And also we aim to use spiking neural networks, which are promising for audio signal processing and also bringing the processings to on-edge processing. And maybe for neonatal and for infants newly born, we could integrate a microphone with a platform, which we are right now working on it for healthcare applications, to do the predictions on edge and online and send the results to the parents. For example, if they have their cell phones, we can send them the results to their cell phones, and then they can wirelessly in their rooms inform about their baby's status. So we automated baby cry detection, and this would be helpful for new parents. And we did a reliable baby cry classification with nested cross-validation and ensembling, and we achieved 94.88 accuracy, percent accuracy on 5 different needs, and around 99.49% with 2 guesses. Thank you very much for your attention. These are my references. And this is again the QR code of the paper. And if you have any questions and want to have a chat with me, please send an email to me and I will be happy to answer.
Subscribe the channel to get instant updates of our publications.